All right, this is part B for homework 2 for separations, and so we're going to go ahead and look at the NRTL activity coefficients for a multi-component mixture. And so we're going to use JAX automatic differentiation of the excess Gibbs energy expression of the NRTL model, and then we are also going to do a direct calculation from the NRTL activity coefficient model. And then after that, we're going to go ahead and calculate the activity coefficients for a specified mixture with 3 different components in it using each of these methods. Okay, so as always, I've got my import up here, and then I have my properties. The mixture that we have is going to be isoproanol, water, and toluene. So I'm just pulling that data right there. And what we want to do first is the JAX automatic differentiation of the excess Gibbs energy expression of the NRTL model, aka this is method 1. So we'll define a function, call it NRTL excess G for the excess Gibbs, and these will be our inputs. And before I get too far into here, I'm going to try to pull up an NRTL example. So this is kind of what we're basing off of. So this right here is an activity coefficient. We have our liquid composition, our tau, which is a binary parameter. Same with this alpha. And so an activity coefficient, this is just from Wikipedia, is a factor used to account for the deviation from ideal behavior. So previously we were assuming ideal behavior, and now we are not assuming that. So that is why we need these activity coefficients, and NRTL is just one way to do this. There's many other methods, but we're doing this one today. And so this is kind of what we're doing. The excess Gibbs free energy is determined to be this excess Gibbs free energy divided by RT is equal to this summation right here. It's a large summation. And for a general equation, since we have 3 components, I believe that was the photo I had earlier, but this is what we are doing, specifically looking at these equations as well as this one up here. So I'll keep this open in case I need to reference it, but I did want to give some background on that. So first we're going to do this tau right here. Tau is equal to P dot NRTL. Again, these are all things that I'm calling from this import. Luckily, that's all already done. But yeah, so P dot NRTL, taking our properties, underscore A. That's our A right there. Plus P dot NRTL underscore B divided by T here. And we keep going, NRTL underscore C. And we're actually doing the log for our C. And that's because we don't have this term right here. And then finally we can add P dot NRTL underscore D times T. The excess Gibbs, we're going to say G is equal to, remember that J and P is JAX NumPy, so it just makes things work quicker with the automatic differentiation, and then it already has like all the same capabilities as regular NumPy. There's just a few differences that you have to watch out for. So J and P, doing the exponent, of P, this is negative NRTL alpha times tau. As you can see, we have the negative alpha times tau, and again, we're literally pulling it from this import. For a shortcut, we're going to say tau g is equal to tau times g, and tau g excess, the excess Gibbs, I'll do an underscore there. And this is where I have to make sure that I don't screw up because I will show you why, but we are doing the einsum, and I'll explain in a minute what that means. J I tau g x. And what this is going to do is it's going to perform a summation over the index of j. So in the NRTL model, we have to calculate how much of the surrounding mixture basically affects each component. But we're telling JAX to take the interaction of component j with component I and to multiply that by the actual amount of component j present, this x, and then sum up all of those j interactions. So what this is doing is calculating the total mole fraction weighted interaction or pull that this is having, basically the non-ideality that is occurring. And it does this in all one single step rather than having a for loop. You could do a for loop, but this just does it all in one line, so it's a lot quicker and just easier to write and read. And a similar thing here, G, our Gibbs excess, JNP, another einsum. We're doing Ki, and just like here, Ki, this time using this Gibbs that we provided an equation for, and the composition right there. And notice that we're using x's. That is because we are doing NRTL, which is a liquid model. And then what we finally want to return is basically this equation right here. So we're going to return the sum of x times tau g excess divided by g excess. And we want to calculate the partial derivatives that are needed for the activity coefficients themselves. So, trying to think of another name. That's going to be long, and that's okay. And this is going to be a gradient of NRTL excess g up here. And then this is the argument that we're using. And we were given that this is a 30, 30, 40 molar mixture. So we want to set that as an array. And the temperature is 300 Kelvin. And then gamma, so gamma is the activity coefficient. Method 1 is going to be this JNP dot the exponent of the Gibbs excess gradient, given the x and t from above. And then we want that to show us what it is. So see if it runs. No attribute. I was having a small issue with this tau, but I think I fixed it. It just wasn't pulling these values correctly from the import. But as you can see here, we have the activity coefficients. This first one is for isoproanol, then water, then toluene. Next, we want to do method 2. So I'm gonna shift enter, oops. And this is method 2. So we're going to call this NRTL, X and T once again, same arguments there. And we can actually copy and paste from method 1 our tau G as well as our tau G, rather than retype that out. And we'll do some more einsum. So X tau G is GNP dot einsum JI, I think the tau and the X need to swap, but yeah, that's what okay, it's the same thing, it's similar as what I did up here. I'm actually gonna take this and just call it something different. And then I'm just gonna put a big solver right there. We need X tau G divided by X G. We need to add JNP dot einsum J IJ to I X G times tau minus this right here. And we'll return JNP dot exponent of this equation above. And I'll call this gamma method 2. That is NRTL above, X and T. It should just pull that from there, so I'm not going to copy and paste that. And then we want this to repeat, or not repeat, but print out to us. Oops, okay. So that is supposed to be a lowercase t. And I think that was the only error I had. As you can see, the activity coefficients match, which is always a good sign. I would like to go more into the einsum because I feel like I didn't completely explain that. Basically, einsum will look at the input arrays and we tell it what we want it to do with the arrays. And so we had the input subscripts and the output. For example, here, when we had this, basically it was performing a matrix multiplication, and we didn't have to do it over and over again. So we had a two-dimensional matrix, and basically we're indicating that J is summed out, and the result is a one-dimensional array, I, indexed by I. Einsum is good to use specifically for matrices and doing like larger scale, I guess, transformations with them, you know, multiplication. You can do sums, swaps, again, multiply, diagonals, a lot of different things. And then I also wanted to touch on broadcasting. The broadcasting is what we did right here. Basically, this reshapes our 3-item list into a 1x3 vector. And what we really needed it for was we had arrays of different shapes. So this allows us to perform operations between those matrices, even if they're different shapes. So you know, like when you are adding or multiplying, they have to match in a certain way. But basically, it'll expand the smaller array to match the shape of the larger one without making copies. So again, it's a more direct way to do it, quicker way to do it. And again, I think for this video, I'm gonna skip my typical end screen, but what we did was we were able to use the JAX framework to facilitate the calculation of the non-random two-liquid activity coefficients. For the multi-component mixture, we had 3 components, isoproanol, water, and toluene. Our first method was JAX automatic differentiation of the excess Gibbs energy, which we did up here. And then we did a direct calculation from the NRTL activity coefficient model. And then I tried to run through, as well as I could, the einsum and broadcasting semantics, just what those mean and how that works. I would encourage you to look more into it yourself and see if you can directly apply it to something more, I wouldn't say more useful, but like more applicable to maybe you and what you do. And yeah, we calculated the activity coefficients, and what you could do is later on use those activity coefficients to calculate like VLE, equilibrium, and Raoult's law with activity coefficient. Basically, for non-ideal situations, we would need to include the activity coefficients. I don't know if you can see that. Let me see if I can. Yeah. So this gamma 1, gamma 2, we would have a third gamma because we had 3 components. For an ideal solution, the gamma is 1, so that's why it's not typically included in Raoult's law. And yeah, in the next part, we're going to go further using what we did today and generate our VLE graphs. And yep, thank you for watching. Look forward to part C.